All right, mathletes. Number 550. So here we have a rocket launch into space. We're given a function for its kinetic energy. And notice how like K kinetic energy is a function of T, M mass is a function of T, and V velocity is a function of T, right? And so we can rewrite this as just, we can write it like this. And you've probably seen this in physics before, this formula for kinetic energy. And so, but just know, like, and we kind of do this a lot of times when we use implicit differentiation is we kind of think of these each as functions of time, and we take the derivative with respect to time, right? And so this is just kind of showing it in a little bit more of an explicit way. But I'm just going to write it like this because I'm just going to use K prime, M prime, V prime like we normally do. But we know that those things are, dk dt and dm dt and dv dt and so forth. And so anyway, so this will just kind of simplify it, but it means the same thing as this, okay? And so anyway, so m is the mass of the rocket in kilograms, v is the velocity of the rocket in meters per second. Assume velocity is increasing at a rate of 15 meters per second squared. And by the way, just a little real quick side note is notice that the rate of change of velocity is acceleration, right? Meters per second squared is a unit of acceleration. So just to keep that in mind. And so anyway, so that value there is v prime, of course, right? So v prime is 15 meters per second squared. And then it says the mass is decreasing at a rate of 10 kilograms per second. And so we'll call that m prime, okay, 10 kilograms per second. At what rate is the rocket's kinetic energy changing? So they're asking for what is K prime, right? At what rate is the rocket's kinetic energy changing when the mass is 2,000 kilograms, so we'll call that m, and the velocity is 5,000. Okay. All right, so they basically give us everything we need, of course. I mean, that's how it usually works out, I guess. But let's start by taking the derivative of this function with respect to t. So we'll do d dt, okay? And so we'll end up with k prime equals 1/2, and we'll do the product rule here again. And again, I'm referring to 449. And so we'll take this as the f function, as this is the g function. And so the derivative of 1/2 m is just really going to be 1/2 times m prime, and then we'll multiply by regular v squared plus the derivative of v squared, which is 2v times v prime times regular f, which is 1/2 m. All right, so so this is f prime g, and this is g prime f, right? If this is f and this is g, right? Okay, all right, so so now we can plug in those values that we know. We can plug in 15 for v prime. We can plug in 10 for m prime. We can plug in 2,000 for m. And we can plug in 5,000 for v. Oops. All right, and then of course we're trying to find k prime. So nice thing about this one is we don't have to manipulate. We can just plug all this stuff in and just evaluate, right? I'm just gonna. All right, so. And you can plug this straight in your calculator if you want to evaluate, or you can work it out in your head or on paper, however you'd like to do this, okay? All right, so we end up with 275 million. All right, and this comes out to 125 million, and this comes out to 150 million. So when you add those together, you get 275 million. And so here's a little bit of a tricky part that I almost missed, which is it says kinetic energy in joules, right? So this is actually joules per second that we have here, right? But then it says give your answer in megajoules per second, which is equivalent to 10 to the 6 joules per second, right? So basically 10 to the 6 basically takes care of all these zeros. And so megajoules per second will be 275 megajoules per second. So 275 megajoules per second. All right. And that's our final answer for that one. All right. Let me know if you have any questions or if you see any errors. And you can also comment on Flipgrid. And thanks for watching.